name is Andreas Schäfer. I'm a professor here at the Energy Institute in Energy and Transport. And I'm here because it's my privilege to introduce tonight's speaker, who is Tony Evans. Tony is a lecturer in energy and air transportation at the Energy Institute, and he has over 15 years experience in that area, namely modeling air transportation systems. He has published widely in that area, along with aviation environmental impacts, airline operations, airport capacity issues, air traffic management, and everything you can think about that has to do with air transportation. He was previously a research fellow at the University of Cambridge and at MIT and at NASA Ames Research Center in California. Tony has 2 master's degrees from MIT and a PhD from the University of Cambridge. And we are very much looking forward to Tony's presentation tonight, of course. But before we can do that, I have to convey a couple of housekeeping rules. Well, first of all, Tony is going to talk for 45 minutes. If you have any questions that relate to understanding his presentation, I'm sure Tony will be happy to take them. If you have questions that lead to issues that are sort of related or longer term implications, then perhaps better ask at the end of the presentation. Then after the Q&A session, as usual, there will be an opportunity to socialize next door. There are some snacks and drinks. They're good, I tested them before. And what am I supposed to say also? Yes, at the very back of the room, I have to identify volunteers that are happy to lead you out of the building after 7 p.m. because that's the time when the doors close, or lock, better to say. So, Julia, you are in the back, so if you raise your arm, then you're one of them. And Soterius, who is next to Julia, is another one. Soterius, why don't you raise your arm? So these are the 2 key volunteers who will be able to lead you out of the building after 7 p.m. But if you stay close to a UCL member, then I think the chances are good that you won't have to sleep in the building. Here are still seats in the very front, so don't be shy, just come up before this opportunity is exhausted. Tony, the floor is yours.
Thank you, Andreas. So today I'm going to be talking about whether technology is enough to mitigate the climate impacts of aviation. I'm going to start off with a quick introduction to the topic of aviation environment generally, and then I'm going to talk a little bit about the Aviation Integrated Modelling project, and then I'm going to try and answer that question about whether technology is enough by looking at 3 case studies. The first one is going to look at the marginal abatement costs associated with different technology and operations options. And then we're going to have a look at how these cost changes may impact the system, how the system may respond to them by trying to quantify the rebound effect in the aviation sector. And then I'd like to bring this all together in a system study where we try and simulate the system-wide carbon and climate impacts of a number of different CO2 mitigation measures. Okay, so as I think we all know, aviation contributes significantly to the economy. The Air Transport Action Group estimated this year about 3.5% of global GDP. But of course, aviation also has negative environmental impacts and particularly climate impacts. So an estimate is about 2 or 3% of global anthropogenic CO2 emissions are from aviation. But as you're probably all aware as well, CO2 is not the only problem when it comes to aviation. There's a number of other impacts. I'm sure many of you will have seen this chart before from David Lee. At the top is the radiative forcing due to CO2. And as you can see, there's a number of different emissions that have different impacts. The net NOx impact is significant, and then the contrail impact is significant. Contrail-induced cirrus is also significant, but the uncertainties on that are still fairly large. But the result is that the radiative forcing due to aviation, including the non-CO2 effects, is significantly higher than just due to CO2. So there are non-CO2 effects, and these are important. David Lee reports that about 3.5% to nearly 5% of global anthropogenic radiative forcing is due to aviation. So that includes the non-CO2 effect. But this is 2 to 3%, 5%. These are not enormous numbers. So why is there significant concern about aviation and its climate impact? That's really because aviation is growing very fast. Airbus and Boeing predict about a 5% per year growth rate. Now, aviation, the energy intensity of aviation has decreased significantly over time. So, and you can see that by looking at this chart, which shows fleet level energy intensity from 1970 to 2010. And you can see there's been a significant decline in energy intensity for aircraft. But you can also see that there's a plateauing effect. And the question is, as we go into the future, can we continue to reduce the energy intensity of aircraft, and particularly of the fleet, at a rate sufficient to offset that growth in aviation that we're seeing? Now, if we look at some historical data for the EU from 1990 to 2007, so far we haven't been doing that well. So this is a chart showing different industries, and you can see that everything's showing a decrease with the exception of transport, international aviation, and international maritime, and particularly aviation is showing more than 100% increase over that time period. So clearly the reductions in energy intensity that we've been achieving over this time period have not been sufficient to offset the growth. And this, of course, is why aviation is a target for emissions reduction policies, and the inclusion of aviation in the EU ETS is our obvious example. So what kind of mitigation measures are there for aviation? Well, we've already mentioned economic, so inclusion of aviation in the EU ETS, for example, and the development of a global ETS or market-based measure to deal with aviation is currently being dealt with by ICAO. Now, the idea here is that you're going to increase the costs to the airlines, and ultimately some of this will be passed on to passengers. So this reduces passenger demand slightly, or it reduces the growth rate in passenger demand, but more importantly, it's stimulating other measures. So that's really what we're after, is to stimulate other measures. And a number of these measures are technological. So varying from retrofits, being fitting aircraft with blended winglets, or new aircraft designs, new aircraft materials such as composites on the 787, more radical design changes such as open rotor engines, and I'll show a couple of pictures of these later, and even more forward-looking design changes for the aircraft such as blended wing bodies. Alternative fuels is also a very important technological development. There are also operational developments, and this is particularly on the air traffic control side, so continuous descent approaches and other procedures that reduce your fuel burn operationally and improve the efficiency of the air traffic system. And there's also changes that airlines can do, so altering their cruise speeds so that they coincide more with fuel optimal speeds as opposed to cost optimal and lightweighting and such like. Now, there's a number of different measures, and the best results are likely to come from a combination of these measures. There's no real silver bullet, so to speak. The best solution is going to come from a number of these measures. And this is where the complications arise, because the measures can interact, and certainly they're not necessarily additive. So an obvious example is if you apply an engine upgrade kit and then you re-engine the aircraft, you're not getting the additive benefit of both of those. There's also other effects, such as introduction of new technology can cause changes in your operating cost, and this may play through the system to have other effects. For example, reductions in operating cost could lead to reductions in fares if they're in a competitive environment, which could ultimately lead to an increase in your demand. So then you're getting this rebound effect. There's also a number of trade-offs. So an obvious example is contrail avoidance. If you introduce air traffic measures to route aircraft around regions of airspace in which you have contrail formation, you're burning extra fuel in doing that, increasing your CO2 emissions. So there's a trade-off in terms of climate impact there. There's other trade-offs as well in for example, the combustor design in jet engines with NOx production and CO2. Also importantly, we don't know what the future holds. So there's a number of uncertainties regarding future populations, income growth, particularly oil price and carbon prices. And these all have a significant impact on how these different technologies would enter the fleet, what rates they would enter the fleet, which technologies and how would compete with each other and how they would do that. So this really suggests that there is a need for integrated assessment modeling, and this was really why we started the Aviation Integrated Modelling project. This was started at Cambridge back in 2006, so a few years ago, and the objective was to develop a policy assessment tool for studying the interaction between aviation, environment, and economics. And we've used this model to do a number of global studies, a number of regional studies, and looking at various different timescales. Now, I'm not going to describe each module in detail, but I'd like to talk you through how the model works. We use different modules to model different elements of the air transport system. So for example, down here in the bottom, we've got the air transport demand model, which does exactly what it says. It predicts origin, destination, passenger demand between city pairs. We use a gravity type model for that, and we estimate parameters for that for different world regions and for different stage lengths, so short, medium, and long haul. This outputs to an airline and airport activity module, which models how the airline chooses to serve that demand. So scheduling, what type of aircraft they're going to operate, what kind of flight frequencies they're going to operate. It also estimates flight delays on the airport vicinity. Now this takes significantly from the aircraft movement and aircraft technology and cost module, because in the aircraft technology and cost model we introduce new technology, and we also model fleet turnover. So how is existing technology being retired, and how is new technology entering the fleet? What rate is that happening at? And this is of course a function of fuel price and a number of other things. Now, there's also important feedback loops within here. So for example, as I said, with a rebound effect, you have a reduction in your fuel burn with a new technology. This leads to changes in operating cost, changes in fare, which then feeds back into the air transport demand module to affect passenger demand. So a reduction in your operating cost could lead to an increase in your passenger demand. So we model these kind of feedback loops through the system. We also output, particularly the flight schedule, to the aircraft movement module. And this is where we model the airborne emissions distribution across the world. This is where we capture air traffic control inefficiencies. So we've estimated different inefficiency factors to describe the deviation from a wind optimal routing. And we've estimated different parameters for different world regions. And then these can, of course, change with time as new air traffic procedures are introduced through the Next Gen program in the US or the CESAR, Single European Sky program in Europe and other regions. These four modules on the left then output to three impact modules: global climate, air quality and noise, and regional economics. Global climate module, we have the capability of modeling this in a few levels of detail, very high level of detail, using the global climate model, less level of detail with chemistry transport model, but then we use a parametric model primarily, which is based on runs of the chemistry transport model. And this allows us to do much more rapid processing. We've also got an air quality and noise model. The air quality model is based on some work that Stephen Barrett has done, who is now a professor at MIT. And it's a rapid air quality model. It models emissions dispersion, atmospheric chemistry in the vicinity of the airport to give us local air quality contours. Noise model, we use industry standard tools for that. Regional economics, we then estimate environmental costs, particularly associated with air quality and noise, and then environmental benefits coming particularly from the demand flows that we're estimating, and we can compare these. Economic benefits. Now, we can then apply policy levers to each of the modules on the left. So whether it's evolution of the air traffic system, or changes in the airport capacity, so adding a runway at a key airport or not. Regulation, so forcing certain technology to come into the fleet. Economic instruments, an ETS or passenger duty. And then we can model how these effects play through the rest of the system before outputting to the impact modules. Now the scope of the model is 95% of the global scheduled revenue passenger kilometers, it's shown there. As I said, I'm not going to go into detail on each one of the different modules. There's quite a lot of detail in how we do each model, the modeling in each module, and you're welcome to talk to me afterwards about anything that you're interested in. I particularly, though, like to talk about the modeling of airline decision making, and this falls particularly in the airline and the airport activity module, a little bit in the aircraft technology and cost. So the first task here is to predict flight network routing and scheduling, and we have two levels of modeling for this. At the global level, we typically use a fairly simple model that assumes that the flight network routing structure stays the same. Now this is a reasonable assumption for developed regions, but for some of the developing economies, India, China, South America, this is less good an assumption. We assume also fixed load factors, and then we use a multinomial logic model to predict how the aircraft size, the use of different aircraft size categories changes with time as the demand grows. For more regional studies, we have a high fidelity model that actually simulates the airline decision-making process. And what we do here is we maximize profit for each airline and optimize the choice of aircraft and the network. So we do a network optimization. But in order to capture frequency competition effect, it's also very important to simulate a game between airlines. So particularly on very competitive routes, a frequency competition between airlines means that the frequencies that the airlines will offer are quite a lot higher than what you get from a, say, system optimal scenario because of this frequency competition. So we simulate a game between airlines to capture that. Fares we then assume we model them based on a constant rate of return. So if the airlines are making a loss in our base year, they continue to do so. And then finally, fleet turnover. So we model aircraft retirement based on historical retirement curves from historical data. And then the acquisition of new aircraft, we use a net present value model. So the idea here is to try and capture the impact of the fuel price, different technologies that are available to you, as well as the operating costs of those technologies, the capital costs of those technologies, which will impact at what rate they then enter the fleet. And I'll talk a little bit more about that later. So what I'd like to do for the rest of the talk is try and address the question that I posed at the start. Is technology enough to mitigate the climate impacts of aviation? And I'm going to do that, as I said, with these three different case studies. And I'm going to start off with looking at trying to quantify the marginal abatement costs for narrow-body aircraft, particularly looking at technology and operational options to do this. And this study specifically looks at the US domestic narrow-body market, and Andreas Schaefer and I have worked for a while on this, but he took the lead, so I acknowledge that. Now, what do we mean by marginal abatement cost? It's typically defined in this way, so it's the change in your direct operating cost divided by the change in the CO2 emissions mitigated. So units are dollars per ton of CO2. Okay, but there's some problems with this metric because it's a snapshot in time. At a certain level of fleet entry for a certain technology and a certain fleet characteristics, it's really just a snapshot in time. So it becomes difficult to compare different technologies that may be entering the fleet at different times and therefore entering with a different fleet structure. So, as I say, different measures enter at different times, and it is very dependent on what the structure of the fleet is. How many aircraft are close to retirement? What size category are they? Does this correspond to the technology that we're introducing? And it also doesn't account for the buildup of CO2. So what we do in this study is we use a discounted cumulative marginal abatement cost. So over the period 2015 to 2030, we calculate the change in discounted cumulative cost relative to a baseline which doesn't include that technology. And then we divide that by the change in the cumulative CO2 emissions, again, relative to a baseline. So this really allows us to compare technologies to each other for that period 2015 to 2030, taking into account the changes in the fleet structure and also taking into account that different technologies may only come into the fleet limited. And it also takes into account how quickly the technology will come into the fleet. Speaking of aircraft stock modeling, so in the fleet structure, there's different cohorts of aircraft that have different fleet ages. And the energy intensity for each age cohort, so to speak, is going to be different. It's a function of what aircraft type are of that age and what type of operations they're being used on. Now, as you modify each age cohort with retrofits, for example, or retirement, etc., this modifies this impacts the fleet energy intensity, the total fleet energy intensity. So it's important to capture the fleet structure and how these different cohorts can be targeted. So, for example, if you've got a retrofit, you're probably not going to want to target aircraft that are just about to be retired. And if you don't account for the fleet age, you're not going to be able to account for that effect. Now, importantly, these effects propagate over time, of course, and it allows us also to align the retrofits with the maintenance schedule. So certain retrofits are significant and they require C checks to make the change. They can't just be done on the line. So this allows us to take that into account as well. There's a number of uncertainties here, though. Firstly, simply the fuel savings potential of the technology. There's a lot of technologies that we're still quite uncertain what potential they will have. Even more so, what's it going to cost? Operational cost as well as capital cost. This is highly uncertain. Also, associated with the cost, there's a number of costs that can often be ignored. So, for example, if you consider increasing your load factor, one of the costs to the airline of increasing load factor is passenger reaccommodation costs go up. Because if that flight gets cancelled, well, flights behind it have higher load factors. There's fewer seats on which to accommodate those passengers that are now cancelled. So you really need to be quite careful about capturing as many costs as possible, and this is particularly challenging. It's also not always clear the extent to which some of these fuel savings technologies have already been adopted. So for some of the near-term ones, how much are they used already? And then also how to deal with ancillary benefits. A number of these technologies have benefits besides just being reducing fuel burn. So how do you account for these? Okay, so let me just go through a number of the technologies. On the aircraft technology side, you've got a number of retrofits, things like carbon brakes, electric taxiing, blended winglets, new lighter seats, and this can give significant weight reductions, to slightly larger changes such as new engines, Pratt & Whitney's geared turbofan, or even more revolutionary open rotor engines. On the aircraft side, you've got new aircraft designs coming in, so more evolutionary designs such as the A320neo and the 737 MAX, more revolutionary designs such as an aircraft that's optimized for use with open rotors, so optimized to fly slightly slower, higher aspect ratio wings, etc. And what we've done is we've built up a spreadsheet model that accounts for all the assumptions that we've made for each one of these technologies. So this is just a snapshot from that. So you can see there's obviously a lot of assumptions that we have to make about introduction year for these different measures. In the case of retrofits, what maintenance check does it apply to? Fleet potential, or application potential, how much of the fleet could you at most apply this technology to? Fuel burn reduction, as I've discussed already, capital costs, direct operating costs. And then you can calculate your payback time. So how long is it going to take to pay off that technology, given the operating costs and such like. And you can see that that varies quite significantly. So you've got 15 years for the re-engineering, whereas you've only got 1 year for the carbon brakes. So it can be quite different. And then you can calculate a mitigation cost in terms of tons per dollars per ton. We also model synthetic biofuels or synthetic fuels. We're particularly interested in cellulosic biomass. One of the key assumptions here is what is your feedstock cost? And so we use some chart like this, where we basically assume that initially the feedstock cost is relatively low because you can use easily available feedstocks such as industrial waste, waste from the logging industry and such like. But very quickly those costs are going to go up because you use up those easily available feedstocks. But over time, the expectation is that these costs will come down. Now, I want to stress that this is not the fuel cost. You usually add the $3 per gallon for the processing cost on top of that. Interestingly, if you look at the current US domestic narrow-body jet fuel demand, it's actually still pretty low. So you can actually, with synthetic biomass, you can supply the US domestic fleet. But obviously that will cease to be the case very quickly because of the growth. Operational options, again we model a number of different procedures, so single engine taxiing, optimized departure procedures, optimized approach procedures such as continuous descent approaches or dynamic descent approaches. Also improvements in the en route portion of the flight, so improving your lateral inefficiencies with the introduction of ADS-B technology, for example. Also improving your vertical profile and your speed profile, and these can all reduce your fuel burn for the operations. And again, we make a number of assumptions about the costs of these technologies and the potential, and I'm not going to show you the chart, but if you're interested, I can send it. Then finally, we look at a number of different airline business strategies that could mitigate CO2 impact. And this can be reduced fuel tankering. A lot of airlines tanker fuel because of cost differentials. Parking the aircraft early, so early retirement. Better matching of aircraft type to mission. So this is where you've got a flight that has a relatively low load factor. You could operate that more efficiently with a smaller type, such as a regional jet. Increasing load factors, as I mentioned earlier, generally. Engine washing, and then surface polishing as well. Obviously, they don't actually use pledge to polish aircraft. And I mean, so for a number of these, some of the costs are quite difficult to quantify. So, for example, better matching of aircraft type to mission. A key cost is by doing that, you're increasing your load factor, so your passenger reaccommodation costs have gone up significantly. Before you had flights that were half full, so plenty of space to reaccommodate passengers. Now you've got flights that are almost full and no space to reaccommodate passengers. But there's also costs associated with fleet commonality. So a number of airlines operate one type for the reason that the maintenance costs and the training costs for their crews are reduced. And it gives them a lot more flexibility. As soon as you then say, well, we now want you to fly regional jets as well, that means these costs go up. And those can be quite difficult to quantify. So what's the result? This is a marginal abatement cost curve. On the x-axis is the cumulative abatement potential, and then on the y-axis is the discounted cumulative marginal cost. So everything underneath the graph are measures that you would expect airlines or manufacturers to be pursuing. They're cost effective at the existing oil price or fuel price. Measures above the graph, they would need an increase in the fuel price in order for them to be cost effective. So that's either simply the fuel price rising or something like emissions trading causing the effective fuel price to rise. Now, these marginal abatement cost curves have been done before, and there are a couple at least for aviation. Typically, exclusive, they only plot marginal abatement costs, not the cumulative abatement potential, so cumulative cost, which is one change here. But also, this work is well validated by the fact that all the technologies that are underneath are actually indeed technologies that we know airlines are starting to pursue or that manufacturers are starting to pursue. So that's a good validation, and we've tried particularly hard to be rigorous about the costs. So I think this is a significant improvement on some of the costs generated in the past. But as I said, it is a challenging cost. Okay, so we're getting about 400 million tons of CO2 mitigated, not quite, with all the measures. And this compares to the reference over this period of 2 billion tons of CO2 that we've estimated. So that's about 20%. So it's a sizable contribution. And if you plot that on that curve that I showed you before with fleet energy intensity, the top line there just shows what you'd get if you simply did fleet turnover with existing technology. And the lower one shows that with a combination of all these measures that I described, you do actually get a sizable reduction. So you are able to continue pulling that chart down, which is very positive. However, there's a key uncertainty, and that is the growth rate. What kind of growth rate are we expecting in this case, in the narrow body fleet? Any growth rate higher than 2.5% to 3% per year means that you're no longer getting carbon neutral growth. So that the 2030 emissions would equal the 2010 emissions at about 2.8% growth. This is taking into account all the measures I described on the previous chart. So any growth rate higher than that, you're not getting carbon neutral growth. Anything below that, and you are getting carbon neutral growth and better. If you only take the measures that are cost effective at the current fuel price, the cutoff is about 1.5%. So any growth rate above 1.5%, and you're not getting carbon neutral growth. So that's one of the key uncertainties. So to summarize the conclusion of this specific case study, we identified a number of mitigation options, and a lot of them do appear to be cost effective at current fuel prices, and are indeed being pursued by industry, which validates the results quite well. Obviously, if you see a technology that is highly cost effective on your marginal abatement cost curve, but airlines aren't pursuing it, then you realize you're missing some kind of costs. As I said, the mitigation potential is strongly dependent on the fleet growth. This has a big impact. There's also a number of other uncertainties, particularly with what the costs are, the capital costs and such like. So there are a lot of uncertainties. And some of the results can be quite sensitive to those, but not all. Okay, so that suggests that there is mitigation potential. The question is then, how is the system likely to respond to that? And to start answering that question, I'd like to do a second case study, which is to quantify the rebound effect. Okay, so first of all, what do I mean by the rebound effect, just to clarify that? Define it as the partial offset of energy efficiency improvement potential due to a reduction in the marginal usage costs, and that's typically associated with consumer demand. So you've got a new technology that's reduced your fuel burn, you're reducing your operating costs in a competitive environment that's reducing your fares, so your demand is going up. Now, for the aviation sector, it's quite difficult to estimate this from historical data, simply because the improvements in fuel burn have been pretty incremental over time, and the entry of technology into the fleet is very slow. Aircraft stay around for 30 years, So it's very difficult to see these changes in fuel burn and pull out the rebound effect from historical data. But we have models that can simulate these effects. Particularly I was talking about the regional model that we use to simulate the airline response to different constraints. So we can use that to try and quantify how the system would respond to changes in cost. We do this, so the study I'm going to show you now is for a network of 22 airports, so it's a relatively short, small network, but it's the 22 dominant airports in the US. So these are the results. Now, on the x-axis is the reduction in fleet energy used per seat kilometer, and then the y-axis is the change relative to the 2000 baseline for these different variables. Now, the bottom one, this light green line, is fleet energy used per seat kilometer. So that corresponds directly to the x-axis. So a 5% reduction is a 5% reduction in the fleet energy use. And the reason I've included that is because if you had no rebound effect, you'd expect the system energy use to lie on top of it. But you don't. The system energy use declines at a slower rate than the fleet energy use per seat kilometer, which suggests that there is indeed a rebound effect. This is, of course, because the costs are lower, which leads to a reduction in fares, which is the dotted black line there, number 4. And that leads to an increase in your passenger demand, which is the dashed blue line, number 2. So there is an increase in demand, this demand rebound. That in turn leads to an increase in your flight frequencies. The airlines respond to the increase in demand to increase their frequency. And that's actually slightly higher than the increase in demand because of the frequency competition effect that I described earlier. Because airlines are competing by frequency, if you change the costs, the Nash equilibrium that they reached in the game changes. So you reduce your costs, airlines are now able to compete more by frequency than they were before, so they add on an extra flight. And of course, everybody does that until they reach the Nash equilibrium again. So that's at a slightly higher rate. That, of course, increases your congestion, which is the orange line at the top, which is an exponential response. So you get an increase in flight delays, and of course, the passengers will respond to that, and it increases costs to the airline, so we have to feed that effect back in. The result is that we estimate a rebound effect of about 18%, and this includes the demand effect as well as the frequency competition effect, and also these mitigating effects of the delays, and also there's also a slight increase in aircraft size that you see as a result of this as well. This result is obviously specific to the network that we modeled, US domestic network on the busiest routes, so it may differ. And I should stress that the majority of that 18% is the demand rebound. That's most of it. The other effects are relatively small. Okay, so we talked about different mitigation options. It's clear that changing your operating costs does have a system effect, and so there is a response from the system. So what I'd like to do now is use a case study to bring this all together. So what we're going to do is simulate the system-wide carbon and climate impacts of different CO2 mitigation measures. This is a global study that was done by Philip Kramer a couple of years ago. So thanks to him, unfortunately he's not here, so I can't pass on questions to him. To put this in context, we're particularly interested in biofuels in this study. And the emissions trading scheme considers aviation biofuel to be exempt to have zero emissions for the purposes of carbon trading. Now, obviously, the life cycle CO2 emissions for biofuels are significantly reduced relative to fossil fuels, so this is reasonable, but the non-CO2 effects associated with biofuels are exactly the same as they are for any other fuel. So the question is, if you get carbon neutral growth, do you get climate neutral growth? And therefore, it raises a question as to whether or not aviation biofuel should be completely exempt of carbon trading or not, because it's really the climate impact that we're trying to reduce, not just the carbon. So first of all, the climate metric we use for this study is absolute pulsed global warming potential. The radiative forcing that I showed you at the start, radiative forcing on its own does not account for the different timescales of the different emissions. So we use absolute pulsed global warming potential, so we assume a pulse of 1 year, and then we look 100 years into the future and calculate the global warming potential for that period. We model non-CO2 effects. We specifically look at NOx impacts on ozone and methane, and we calculate this by altitude, flight level, and then we also calculate the impact of contrails and contrail-induced service. And we neglect the other non-CO2 impacts. We also make the assumption that the atmospheric background concentrations don't change with time, which is, of course, a simplifying assumption. Now, the technology assumptions that we apply in this study, unfortunately, this study was done before the marginal abatement cost curve that I described earlier. So we don't include quite as many technologies as we had in there. And we're in the process of running AIM with those technologies. But in this study, we had a drop in biofuel, also cellulosic biomass feedstock based. The assumption was that it was available from 2020, and that we could go up to a 50-50 blend, which is very high, but this study is looking up to 2050. The biofuel production was initially limited, so we're not assuming that in 2020 you can get your 50-50 biofuel blend. We do limit production. We then model ATM improvements by assuming that it gives you about a 4% global decrease in fuel burn. And then new aircraft models, again, this is considerably simplified relative to the marginal abatement cost study. We assume that you get about 1% per year improvement in fuel burn for these new models. And then on top of that, we introduce a number of more revolutionary technologies, including blended bodies and optimized open rotors. And then therefore we make assumptions about when the technology is available, what percentage reduction in fuel burn you're getting, what are the operating costs, what are the capital costs, etc. And then the AIM model can simulate how these different technologies enter the fleet, how they compete with each other, because you may have two technologies, one which has a lower fuel burn but a higher purchase cost, higher capital costs. And depending on what the fuel price is, the uptake of those two technologies may differ. So there can actually be competition between technologies, and we capture that within AIM based on the fuel prices we model. Speaking of fuel price, we have to make assumptions about socioeconomic scenarios, so describing what kind of population growth we're getting, income growth, oil price, etc. And we use 3 different scenarios from exogenous models: the MIT IGSM model, the Stanford Merge model, and the Joint Global Change Research Institute's Minicam model. And this represents approximately kind of a high global demand growth, medium global demand growth, and low global demand growth. We then also consider emissions trading. So we apply a global emissions trading scheme to aviation here. We make the assumption that it's an open scheme, which means that we can reasonably assume that aviation will be a net buyer. So we simply apply the carbon prices as a carbon tax. The levels for the carbon tax we take from these 3 models, and they're in those models they set the carbon price in order to achieve long-term atmospheric CO2 concentrations either of 550 parts per million or 450 parts per million. So the advantage of this is that the carbon price is internally consistent with the oil price, the income forecast, the population forecast. And this is valuable. And then, of course, we assume that biofuels are exempt. So, how does this affect the life cycle CO2 emissions? So this shows the 3 different scenarios. And you can see that there's a significant growth in the baseline, which is no emissions trading or biofuel. So there is some technology uptake in that baseline, but not a huge amount. We then introduce emissions trading, which is the second line in the 3 cases, and you can see there's a slight drop, because with the emissions trading, there's an increase in the technology uptake, with the exception of biofuel, which we then introduce separately. And because we're modeling up to a 50-50 blend, the impact of biofuel is quite significant. And you can see that in all three scenarios, you get these periods of carbon neutral growth. So first of all, this suggests that indeed you could get carbon neutral growth with an emissions trading scheme and with biofuel. But is this climate neutral growth? So this is similar plots for global warming potential. Again, the three represent the three different models. The top three charts represent the first case, so no emissions trading and no biofuel. The second ones represent just the emissions trading, and you can see there's a slight drop in the total global warming potential. And then the third case is with the biofuel. And the most important bit here is that it's still always increasing. Yes, it's a significant decline on what you had even with emissions trading, but it's not climate neutral. So the conclusions from this study is with a 50-50 biofuel blend and emissions trading, your 2050 emissions could reduce by about 50%, and this is due to both a demand reduction in the demand for flying, biofuel uptake, as well as the uptake of these different technologies. And it suggests that carbon neutral growth is indeed possible, although questions about whether it's sustainable in the long term. But of course, we only included a certain number of technologies. New technologies will come up as we progress, so it may be more sustainable than that graph showed at least. And then the reduction in climate impact is somewhat lower. It's only about 30%, as opposed to the 50% for the CO2. And this is looking at a 100-year time horizon. If you reduce the time horizon to, say, 20 years, so of course the impact of the CO2 is less significant, and the impact of the non-CO2 effects becomes a higher, a larger proportion, you end up with only about a 15% reduction. So there is potential for biofuel to prevent, I should say carbon neutral growth. So there's potential for biofuel to provide, potential for biofuel to provide climate neutral growth is limited. I should read my slides. It's challenging. Carbon neutral growth does seem to be possible, but the climate neutral growth is more challenging because the biofuel doesn't really give you any benefit on the non-CO2 effects. And this questions whether some of the emissions trading exemptions for biofuel are justified. Obviously, I think you should still have exemptions, but whether it should be completely exempt or not is a different question. Okay, so that brings me to the conclusion, is technology enough? And of course the answer is depends. CO2 emission mitigation is highly dependent on fleet growth rates, as I showed. It's also highly dependent on technology adoption. So the technology adoption is very dependent on what purchase price you've got for the technology, the fuel price, competing technologies, as well as your accounting assumptions. So higher fuel prices would mean greater uptake of technology, which would go further to mitigating carbon. Technology adoption can also be sped up with policy intervention. So introducing an emissions trading scheme is essentially increasing the fuel price. So more technology will be adopted, and will be adopted at a faster rate. Carbon neutral growth may be possible, but only under significantly higher fuel prices. And this is important. Whether those high fuel prices come for simply the price of oil is going up, or whether it's because of an emissions trading scheme that applies a reasonably high carbon price, carbon neutral growth is only really possible under a scenario in which you've got higher fuel prices. The prices have to be sufficiently higher to allow the adoption of all these technologies. Carbon neutral growth, however, does not mean climate neutral growth, and that is more difficult. Okay. Thank you very much. If you want more details on everything we presented, the aim.project.aero is the project website that you can also get in contact with us. So I can open it up for some questions.
Yes, please.
Hi, my name is Becky Moorhead. I'm at Imperial College. Thanks very much for this talk. It was really interesting, especially the last bit about biofuels carbon reduction. I've got two questions really. One's about your marginal abatement cost curve. I've been doing a review of biofuel conversion technologies and their associated costs for a climate hit project. And I noticed on your cost curve that the marginal abatement cost of second generation biofuels was pretty much neutral. And I was just wondering how you calculated that, because from the estimates that I've been looking at, the cost of aviation biofuels are expected to be around double the selling price of kerosene. And actually they're selling for a lot more than that at the moment. So that was question number one.
Yeah.
And question number two was, I was just wondering if you've done any work, you were going to do any work looking at if an appropriate level of ETS carbon price was applied to biofuels, how would that then impact sort of their uptake and then the the climate impact reduction?
Within Europe specifically or globally?
I'm interested in both.
Okay. So let me go back to the costs, the cost curve. And actually, so the assumptions, the main assumption on, and correct me if I'm wrong, Andreas, the main assumption on the cost is based on this curve. So a lot of it is based on what feedstock we're using. So cellulosic biomass, there is quite a lot of waste material that, at least in the near term, is cheap, and there's enough of it at the moment to actually fuel the narrow-body fleet in the US. So there's a lot of waste material, but of course that's not going to be growing at the same rate that aviation is. So very quickly you're going to use those costs, and your other costs are going to climb. And do you have anything to add?
It is certainly very much region specific. I don't know what part of the world you were looking at. These are costs for the US, which are taken from the Oak Ridge billion-ton study. And as Tony explained, there is a lot of stuff around that is a very low cost, which is residuals from agriculture and industry. But eventually, if you want to supply more than the aviation sector, then of course your costs are up. But the spreadsheet model allows you to enter the whole range of assumptions, and then shows you how the cost curve may shift to the left or the higher level, so depending on the assumption.
So this was one of the objectives in doing this marginal abatement cost curve, was to make it open to other assumptions, because there are a huge amount of assumptions that you have to make in this kind of study. And if so, we could plug in higher feedstock costs or processing costs, for example. But I think it does vary a lot by region. And specifically, cellulosic biomass in the US has got initially reasonably low feedstock costs, but that may not apply, or does not apply, definitely, to another feedstocks. Your second question was about?
Yeah, I was just wondering what the sort of feedback impacts would be if biofuels did have a smaller carbon price attached to them.
So obviously, the cost to the airline is higher because they're paying a higher price for their fuel. So if essentially the reduction in cost is less, so some of the feedback effects, you would get slightly less rebound, which would help your CO2. But of course, it's also going to increase your costs to the airline. I mean, it's increasing your effective fuel price, so it could actually induce other technologies. So, in this is at $3 per gallon. If your fuel price was higher, then more of these technologies would be adopted. So you actually by charging a little bit some carbon tax for your biofuel, you would actually be increasing the effective price, and therefore some more technologies may be adopted.
Okay, thank you.
Yes.
A question about the limitation at the end, 50% reduction. Presumably that doesn't include any growth in demand.
So that's a 50% reduction relative to the 2050 baseline equivalent. So let me go back to the chart.
So baseline equivalent would
It's not
include
saying,
demand, right?
yes, it's not saying a 50% reduction relative to 2010. So I mean, it's that chart
Yeah.
there. So this is 50% of that. So what you're saying is, what we're saying is that introduction of biofuel and the ETS could reduce your 2050 emissions by 50%, but that definitely doesn't mean you're getting carbon neutral growth relative.
Yeah, the other question I had, you've got obviously got carbon neutral growth for a short period. Then.
Yes.
So you said it was possible, but what about the period after?
Well, that's exactly it. And I mean, I should stress that we model a certain number of technologies, and in 2030 there will be other technologies that we haven't thought about. But it is a very real point, and it's a concern that, okay, yes, we could get carbon neutral growth initially, but maybe it's not sustainable long term, because the demand for aviation is expected to continue to grow. And I mean, particularly for this one, it's actually a relatively small period of carbon neutral growth before you get this increase. And as I say, this is a 50-50 biofuel blend, so this is a lot of biofuel.
There's one more question about biofuel and the displacement of the amount of biofuel we need to grow, and we taking that into account anyway, like food.
So with cellulosic biomass, the assumption is that it's not replacing food. But for the future, so that chart I showed earlier with the different costs, obviously the shorter term costs are from waste material, from logging industry and manufacturing and such like. But as you use up those costs, well, where is your cellulosic biomass going to come from in the future? And then you do start getting questions about, what else would you be using that land for? So it's a real question further down the road. But in the immediate case, so that cellulosic biomass was particularly picked because it doesn't replace food. Is that fair to say that?
I think so. Totally, you can run the Q&A session.
Any other questions? Yes.
Just on the question of fleet growth,
Yes.
Sokolov has written a paper recently, may have seen it, on the effect of the new fleet of coal and other fossil fuel plants on the future cumulative carbon emissions that are going to be built in. It's actually quite a sophisticated model he's used with retirements and all the rest of it, and saying we're able to predict what the cumulative emissions are going to be just for the plants that we're committed to now. It strikes me that you can do exactly the same for the committed orders from
Right.
Boeing and Airbus, etc., at the moment, and you can actually build that into the model, and you can assume the Chinese fleet is going to rise dramatically. You can actually build that in and get a very good idea what future cumulative emissions are going to look like.
Definitely, and that doesn't give you that long, unfortunately, because the orders, from orders to actual delivery, it varies significantly. So for something like a 787, the first orders were a number of years before delivery, but for some of the types that are already in existence, the time period is a little bit shorter. But certainly that could give us a picture, to 2020, or probably not, maybe not quite 20. Well, no, probably 2020, maybe even a little bit further than 2020. The orders would give us that picture, certainly. Obviously, when there are, airlines do sometimes cancel orders, and sometimes, at least under extreme circumstances, they will even park aircraft. But with our assumptions, we're not taking that into account. But that's a good point.
You will also withdraw aircraft from the fleet, and we don't know the rate of withdrawal, which is important.
That is a good point. Fleet retirement rates we can get from historical data, and they are actually seem to be relatively insensitive to oil price. So you can get some idea of what the fleet retirement rate is as well. But that's an interesting point. Thank you.
Owen Bellamy from the Committee on Climate Change. I was quite surprised to see the abatement costs were negative for the majority of the abatement.
Mm-hmm.
And I wondered whether some of that was because I think the time frame was only 2030. If you were looking on a 2050 horizon,
Right.
would that change that assessment? Because I wasn't sure whether there were any
Well, I think
radical type
I mean, the
options
time,
in there, which
increasing the time scale, you get more fleet entry for the various technologies. The mitigation potential will increase. I mean, all these technologies under the graph are being pursued already. So, I mean, if you look at them, increased load factor, we've all experienced that. Reduced contingency fuel. I mean, I can go through all of them. They're all are. I mean, it's validated by what's happening now. Now, because we're looking at the narrow body fleet in the US, we don't consider, for example, blended wing bodies, which is more of a revolutionary design in the future. So that would probably
be on the right side.
be on the above the graph. But I mean, everything that's under the graph is being pursued. I mean, a number of these, and I mean, I won't go through all of them, but pretty much, I mean, everything that's under the graph is being followed and being pursued. The question is then, okay, there's this mitigation potential. How would it be adopted in the fleet? Is there competition between some of these technologies? What's the demand rebound effect? So that one of the things, our next task is to run all these technologies through the AIM model and see how the system plays out and which technologies are adopted and at what rates. But this suggests that there's a reasonable mitigation potential, and we have really tried to be rigorous about quantifying the potential and the costs. But as I say, it's challenging, and there are assumptions, and as I say, some of these assumptions, some of the results are quite sensitive to them. I mean, particularly that one at the end there, that tall one, which is the better matching of aircraft type to mission, is very sensitive to your assumption about fleet commonality costs. So how much does your cost go up because you're operating two types instead of one? And that result is quite sensitive to that. But it's also, airlines are not doing this yet. There isn't a particular increase in regional jets. And I mean, reduced tankering as well on the right. Airlines are still tankering. I mean, that's an obvious one. If it was not cost effective to tanker, airlines wouldn't tanker. So it's reasonably well validated against what's happening now.
Can I add something? Sure. So your concern may apply to the new aircraft, so new engine option aircraft, MAX Boeing, and the counter-rotating propeller aircraft, because we amortize them over the whole economic life of 20 years, which is beyond the 2030 time horizon. But for all other measures, the payback time is below 5 years, at least for those measures that are cost effective, so they're well amortized during that period. Also, if we look at longer periods than the economic life, then these more fuel-efficient technologies, once introduced, contribute to lower CO2 emissions and actually get the opposite effect, that the costs are actually lower if you expand the time horizon.
These are definitely things that we're going to be doing with the model.
Yeah, it's just interesting because it's generally previously been assumed that aviation was a kind of high-cost payment sector. And obviously there wasn't a lot of evidence.
Yeah, there's not been a lot of abatement cost curves generated, and as I say, they are difficult because there's a lot of assumptions.
Well, one question related to that is what is the real baseline? Because if airlines adopt these measures anyway because they're cost effective, perhaps that's the correct baseline to take, whatever you feel.
Yeah, that's true. Should we be even accounting for increased load factor, because the airlines are starting to operate high load factors?
Have you ever run the model almost in reverse to see what level of growth would be?
We haven't, but that's an interesting point. So what level of growth, or maybe what carbon price or something like that would give you carbon neutral growth or even climate neutral growth? Yes, we have not done that, but that's certainly something that we could do. It's an interesting suggestion.
On the biofuels, 50-50, that's quite a lot. It's not just about feedstocks, it's also about producing them. What's your assumptions on production capability? That it's just that, or do you have a model of how that is rolled out?
So the assumption is that we assume $3 per gallon for the processing production cost.
There's not so much the cost, but the actual capacity, the plants,
Right.
because they're not there. No.
And absolutely, and for that reason we only assume the 5% market share in 2030.
So yes, that should.
But what we should say is, so we've built a spreadsheet, we're validating it, and then the intention is to distribute it to the public so that everybody can introduce his or her own assumptions and come to different conclusions. But within the range of plausible assumptions, the results shouldn't be too different from what we conclude.
Yeah. So yes, because this is only to 2030, we've only done 5% adoption. And I completely agree that the 50% adoption in the other study is high, even 2030.
Similar but different question. We're looking at technologies that impact internally. What about competitive technologies? For example, the region on those changes of gravity change.
Yes, it's a very good question. We haven't accounted for that. I mean, we use our forecasting of growth is based on population income forecasts, and then the gravity model is calibrated on existing past years. So by definition, it's not accounting, well, it's recent years, so it is accounting for the current level of telecommuting and such like, teleconferencing. But you're exactly right, that is something that we have not dealt with. It's a difficult one to get a handle on, and I mean, I've heard very different opinions on the extent to which that kind of technology may affect air transport demand, because anecdotally I've heard that initially it actually increased demand because you can now do business with somebody on the other side of the world, which you couldn't do before, but you still have to visit them at least once or twice. Now, presumably that would be the initial effect, but in the longer term, you would get some kind of substitution. But it's
And in the context of what would be an optimal growth pattern, then there's policy decision making around encouraging or discouraging different
right.
technologies.
That's
I'm
very
very
interesting.
interested.
Yeah.
There's a context that becomes very useful.
Yeah, no, that's very interesting. Yes.
Yeah, hi, Ian from DEC. Like colleague from climate change, it's fascinating to see the macro below the line, because like that, we've always assumed or been told that it's all very expensive to debate them. So two-part question, I suppose. In terms of some of the less technology measures and like increasing the load factor, how much are measures being taken up at the moment? How much are you seeing being adopted? Is it 100% adoption? Presumably not. And
yes. I mean, this is actually one of the big uncertainties, is even knowing what the current uptake is. Because unfortunately, airlines don't report on their websites or on their environmental reports the extent to which they've started doing single-engine taxiing or using surface polishing, etc. So it is very difficult to quantify that. And that goes back to Andreas's point about, what should the baseline be? Maybe we should take one of these and assume that they're being done, and then go from there. So I mean, you look at all these technologies in the list, and they are near-term things that the airlines are starting to do, but it's very hard to, I mean, it is very difficult to know to what extent they're already being adopted. So we've taken as best an estimate as we can, but with big uncertainties.
Can I jump in? You're too cautious, Tony. I think in a couple of cases, I think we've got a good understanding of what the potential is. Blended winglet retrofit, we know that in the US, virtually all B737 aircraft that are suited for winglet retrofit essentially have been retrofitted. But we also know that the entire Airbus fleet can be retrofitted by exchanging these very simplistic wingtip fences by blended winglets, which gives you a 2.5% reduction. We've got a good understanding about the single-engine taxiing procedure based on surveys.
Yeah.
Conducted at MIT. We've got a good understanding about the load factor and the difficulty probably in achieving that reduction because of frequency competition that you mentioned, which may require additional policy measures to exploit the potential, and so forth and so forth. So there are uncertainties. I fully agree with Tony, but I think you have been too cautious.
Can I ask a follow-up question?
Sure.
In your research, have you come across policy measures that perhaps aren't the economic ones around ETS that would stimulate the airline industry to increase the take-up of these measures?
You mean things like regulation? I mean, certainly regulation has been very instrumental in noise. So, I mean, there's a carbon standard being developed at ICAO at the moment. So that may fall into that category. How effective it is a question. But beyond that, I'm not sure really.
International agreements probably, since much of this is international.
Yeah.
As long as there's no international, unified approach to this.
Yeah. I mean, this is why it's a market-based measure that ICAO is developing, but it's going to be critical how that plays out and the extent to which there is real international agreement on that. And so, I mean, that's critical, but that's a market-based measure, so that's similar to ETS.
So perhaps in the interest of time, so in the airline language, we are running into delays. But we had a load factor here, a passenger load factor that Ryan O'Leary can only dream about, and we were above 100%. So thank you very much, Tony, for your presentation again. And those of you who have the time and the interest, please join us in the next room, adjacent to this one, for wine or non-alcoholic drinks and some snacks. So thank you very much again.